Okay, let's dive back in. Welcome back, everybody. Just a reminder of where we've been, where we are, and where we're going. We are working our way through, we're going to finish today our history of evolutionary robotics, admittedly a short history. And we've been, in the last few weeks, talking about locomotion, because at least in the animal kingdom, the origins of intelligence are deeply entwined with movement. We talked about Linus's question about why don't plants have brains. Not that plants aren't intelligent, but whatever it is that they're doing, they don't seem to need brains because most plants don't need to get from point A to point B. So we're looking at this connection between locomotion and intelligence. We're going to finish that up today, and we're going to then move on to sort of where the field is today. And we're going to look at some of the major challenges in the field. One of the nice things about learning about and working in a relatively young field is there are wide open questions. There are big questions, big challenges that no one has a good satisfactory answer to. We will look at some answers that some researchers, myself included, have tried to come up with to address some of the major challenges in creating autonomous and adaptive machines. Okay, so that's lectures. We're working our way through our assignments. Thank you for most of you getting in assignment 7 and 8 last night. We are closing in on the final 2 assignments. So you're now going to be tackling assignment 9, which is continuing this theme of putting in more and more powerful search methods. So you started in assignment 7 with random search. You swapped out random search and replaced it with the hill climber. Some of you probably noticed by playing around with your hill climber that a hill climber will do what a hill climber usually does, which is get stuck on hills, right? You run your hill climber once, starting with one set of random synaptic weights. It climbs that hill in the fitness landscape and gets stuck. You stop your code, you start it again. It starts with a different set of synaptic weights, which is another point in the fitness landscape. It starts climbing again. Maybe it gets higher, maybe it gets not as high as it did during the first run, right? Simplest thing you can do to get over that is to create a parallel hill climber. So you're going to be doing some parallelism in assignment 9. You all have different laptops and different machines. Some are more powerful than others. Some have more more ability for parallelism than others. It's not going to matter. It doesn't matter how much you parallelize your code. All that matters in assignment 9 is that you parallelize your code. You're going to have multiple starting points, multiple hill climbers that are climbing their various hills in parallel. And at the end of the parallel hill climber, it gives you back the parent, the hill climber that climbed the highest hill. Pretty straightforward. Okay, in order to do this parallelism, there's quite a few steps. No one step is very complex or difficult, but there are a lot of steps. I think there's like 120 steps in the parallel hill climber assignment. So please make sure to get started on it as soon as possible. If you get stuck, come and see me or the TA in office hours. Any question about assignment 9? Question assignment 8? Assignment 7? All good? Okay. So back to lecture 12, where we're talking about our particular form of bipedal locomotion. And us humans, thanks to evolution, have struck a very extreme trade-off between displacement, energetics, robustness, and balance, right? Takes us quite a while to figure out the balance part. Takes us 2 or 3 years at the outset of life to figure out the balance part of bipedal locomotion. But once we get that figured out, the benefit is what? We're also not the fastest animals out there. We take a hit in terms of stability and displacement, but we make up for it with energy efficiency, right? So we started last time by talking about the most energy efficient form of locomotion out there, which is passive dynamic locomotion. And we started talking about this experiment last time where the investigators evolved the body of a passive dynamic walker to walk down a decline with Basically infinite energy efficiency. No motors, no electronics, no sensors, nothing. It's kind of hard to see from this picture here, the decline, but if I go back and forth between these two images, you're going to see in a moment that there are two phases to this experiment. In phase one, they evolve passive dynamic walking down a decline, and then in phase two, they're going to continue evolution. But now they're going to start to fold in the brain. They're going to broaden the breadth of the evolutionary algorithm so that it's no longer tinkering with just the body. Now evolution is tinkering with body and brain and basically keep things going. Continue whatever gate was found for passive dynamic locomotion and turn it into hybrid dynamic locomotion, which is what we do. This particular machine here is going to give a small impulse force. It's going to send some force, the motors are going to send some forces to the joints when the stance leg, the leg with the foot that's on the ground, leaves the ground and gives a little bit of a push. And when the stance leg becomes the swing leg, then the motors turn off and the leg swings forward like our legs do, like the passive dynamic walker's legs do, and so on. Okay. So to start with, since there's no neural network controller to evolve, they're going to set up an evolutionary algorithm to evolve aspects of the robot's body. Just to remind you, this robot has 10 mechanical degrees of freedom, 5 joints in the left leg, 2 at the hip, 1 at the knee, 2 at the ankle, and another 5 mechanical degrees of freedom on the other leg. So 10 mechanical degrees of freedom. In the passive dynamic walker, these are going to be 10 joints, but 0 motorized joints, right? No motors yet. They are going to add on some masses to the robot's body, and evolution is going to play with the position and size of these masses to change the mass distribution of the robot's body. There are actually masses on the thighs, the shank, the foot, and the hip up here. There are some other aspects of the robot's body in addition to the position and size of these masses that they're going to subjugate to the evolutionary algorithm, like, for example, the length of the legs, the length of the feet, the radius of the waist, and so on. The last aspect of the body that they're going to evolve are some springs, and I think this is where we ended last time. We spent a little bit of time talking about springs. The simplest way to model a spring is with just 2 numbers. The stiffness of that spring, you can think of that as the thickness of the steel coil. And then damping, which is how much or how little the spring will return to its rest length after you've stopped pulling and pushing on it. And here are my little cartoons here of what springs with high stiffness, high damping, low stiffness, high damping, high stiffness, no damping, and low stiffness, no damping looks like. We've got 5 springs. We've got 5 springs on each leg. 2 springs at the ankle, 2 springs at the hip, and a 5th spring, which is not shown here, in the knee. Okay, so those are all the parameters. These are all the parameters that we're going to take and now put together in a vector and hand that vector over to the evolutionary algorithm. At the moment, your hill climber is evolving a vector that contains numbers. Those numbers are synaptic weights. In this case, we have a vector of numbers again, but they're body parameters. How many body parameters are we evolving in total? What's the length of that vector? How many numbers do we have here that we're going to include in this vector? Not quite. We've got 5 springs. 10, right? So we have the stiffness and dampness for each, the stiffness and damping for each spring. So we've got a total of 10 numbers. I forgot to mention, hopefully it's obvious, they're going to assume that this robot is bilaterally symmetric. So whatever the stiffness and dampness, the damping is for the 2 springs on the left side of the hip, it's the same thing for the right side of the hip. Everything on the left side of the robot's body is the same as everything on the right-hand side. So we've got a total of 10 numbers here. How many numbers do we have here? 12, right? So we've got these 12 body parameters plus these 10 body parameters. So we're going to see in a moment an evolutionary algorithm that's evolving populations of vectors of length 22. Body parameters, no brain yet. So far, so good? Okay. Okay. There is a little bit of a brain here. There's a little bit of a twist. As we go on through this experiment, we move to hybrid dynamic walking. The robot is gradually going to be controlled more and more by this neural network. It's a bit of a hairball here, but we'll try and untangle it here. We're back to working with a continuous time neural network. You'll notice there's no R here. There are no recurrent connections here. Although now I see some recurrent connections. Okay, maybe it's a CTRNN, maybe it's a CTNN. Doesn't matter for our purposes. We've got 5 motors, which we'll see in the second phase. These 5 motors are not attached to the joints. These motors are attached to the springs. This is actually more biologically realistic than attaching the motors directly to the joints. How so? What biological detail are they folding in by taking motors, connecting them to springs, and springs are pulling on links here, not joints? Think about your own anatomy. What's the biological detail here?
Springs act like muscles, whereas the body acts like the bones.
Close. So the body, obviously, the links are the bones. The muscles, the motors, as always, are muscles. What are the springs here?
Like ligaments or tendons.
Tendons and ligaments, right? Exactly. So your muscles don't pull directly, most of the time they don't pull directly on bone. They pull on springy cartilage, which is tendons or cartilage, which is exactly what gives you part of your energy efficiency, right? We talked about your Achilles heel and how that contributes to bipedal locomotion. Okay, so we've got 4 motors which are going to pull, or we've got 5 motors which are going to pull on the 5 springs on one side of the body. As always in this experiment, what they're showing is what they're showing for just one side of the body. This neural network that's going to control the biped in a moment, there are actually 2 identical copies of this network. One that controls the left leg, one that controls the right leg. We got 5 motors pulling on 5 springs. We have a whole bunch of sensors over here. If you focus for a moment on the postfix, right on the end of the names of the sensors here, you get a sense of the kind of sensors they're sprinkling throughout the leg. We have angle sensors, otherwise known as proprioceptive sensors. They report the angle of a given joint. We have force sensors, which I don't think we've seen before. Force sensors, as the name implies, give us back a reading of how much force is occurring close to where the sensor is sitting. In all the F sensors here, they're placing them directly on the springs, and they're measuring the force in the spring. So let me just back up to springs for a moment. If you think about a spring, remember that it has a resting length. If you don't pull or push on the spring, there's a particular length that it likes to, quote unquote, rest at. If you pull away from it or compress it, there is a force acting on the steel or whatever the spring is made up of. Same thing with your cartilage and tendons. So we got some force sensors as well. We have some rotational and acceleration sensors as well. The rotational sensors are measuring orientation, and acceleration is measuring rotational acceleration. So how much things are rotating or changing their orientation. Okay, so a whole bunch of sensors. As always, those sensor neurons are connected by synapses to hidden neurons. The hidden neurons are connected to motor neurons, and I do see a few recurrent connections here, I think. Actually, these are not recurrent connections. These are connections that are flowing outward from the Cpg neuron. This is a new type of neuron that we haven't seen before. A central pattern generator is kind of like a bias neuron. We saw the bias neuron just before spring recess. The biased neuron just outputs a constant value. A CPG outputs a constant oscillatory signal, some sine wave that has a given frequency and amplitude, and it just produces that pattern over and over again. You have central pattern generators in your spine as well. They're not individual neurons, they're actually small neural circuits. So there's a little bit of a abstraction here. But you can actually wire up a few neurons in most mammalian nervous systems. And depending on how you wire them up, they will spontaneously start to output an oscillation. The central pattern generators in your spine, or at least in your lower spine, tend to produce an oscillation at a particular frequency. What do you think that frequency is? Cast your mind back to the beginning of lecture 11 when we were talking about the biomechanics of locomotion. You have CPGs in your lower spine that are outputting a constant sine wave at a given frequency. What do you think that frequency is?
Maybe your gait.
It's tied to your gait. What's the frequency of your gait? When you leave the room, assuming you walk at an unhurried walk most of the time, what's the frequency? How often does your foot strike the ground? Every second. 1 hertz. The CPGs in your lower spine output a frequency of about 1 hertz, so that most of the time when you're quote unquote not thinking about it, your legs kind of walk your body for you, right? There is a very large unconscious component to locomotion that's being controlled by your spinal cord, specifically being controlled by your CPGs. If you put someone in an MRI, a magnetic resonance imaging machine, that's looking at the brain, not at the spinal cord, there are particular frequencies that you can pick up in the brain. One of the strongest signals in the brain is an oscillatory signal at a frequency of 1 hertz. It's another big piece of the puzzle about how locomotion and thinking are connected. Now, what exactly that 1 hertz is doing or controlling in the brain, nobody knows yet. But it seems to be a particularly important or strong signal in the central nervous system. Okay, one more detail about CPGs, a bit of a gory detail. You probably heard the adage about cutting off a chicken and it keeps running with its head cut off. Why does a chicken keep running without its head? Because its locomotion, its bipedal locomotion, is not controlled by its central nervous system. Its locomotion is controlled, like us, by the CPGs in the lower parts of its spine. Okay, that's CPGs. Okay, as promised, in this first phase of the experiment, we're not going to use most of this neural network, but we are going to use one part of this neural network. We're going to use the CPG. What the CPG is going to do is, most of the time it's emitting a sinusoidal pattern. We're going to assume in this experiment that it's actually producing a square wave, meaning most of the time the signal is 0, but every once in a while it gives a little bit of a non-zero signal and then goes back to 0. And we're going to assume that this CPG is going to control the pacing of the legs. It's going to give 1 pulse to the left leg at a particular point in time, and then half a second later it gives a pulse to the right leg. A second later, a pulse to the left leg again, 1.5, right leg, 2 seconds, left leg, 2.5, 3, 3.5. In this case, the CPG, like the CPG in your lower spine, is going to be the conductor. It's going to tell the leg that it should do something. What that leg should do is not up to the CPG, it's up to the body of the robot. Okay. We'll come back to that detail in a moment. Okay, so the CPG is going to give a little bit of a signal to the passive dynamic walker, and then in this first part of the experiment, the CPG is going to shut off completely. It's only going to give 1 pulse, and then the CPG is going to go silent, and we're going to see how the passive dynamic walker does at moving down the declined plane. We're going to evolve this vector of length 22. We're going to evolve the body of this passive dynamic walker, and we're going to assign a fitness to how good that body is when it receives one pulse of the CPG. You can see that this fitness function is a multiplication of 6 different terms here. The first one is probably the most obvious one. Distance traveled down the declined plane. The better the body, the further that body travels down the declined plane. Why are we not reading about a paper that has the simpler fitness function of F equals D? Why do you think they added on all these other terms?
I think that also optimizes for energy efficiency.
We are not quite at energy efficiency yet. We're assuming in the passive dynamic walker that by definition, it's maximally energy efficient. There's a little bit of energy that the CPG is going to supply into the robot, which we'll see in a moment, but it's an instantaneous force. It's a little bit of a shove just to get the robot moving at the top of the declined plane, and then everything else is passive. So we're not worrying about energy efficiency now. This thing just is maximally efficient.
Because it's trying to evolve like a very specific kind of motion, and so like putting these extra terms on it like limits how creative it might be able to get.
Absolutely, right? Remember the Ministry of Silly Walks, which we saw at the beginning of this lecture. All of these terms here penalize various forms of silly walks. But let's forget the details. We'll get to the details of these terms in a moment. Let's just imagine F equals D. You're starting to work with the hill climber. You're getting a sense of when you allow an automated search process control, it tends to come up with some pretty silly things. If you were to evolve, given the details I've explained so far, if you evolve this thing just with F equals D, what kinds of motions down the declined plane do you think you would get?
You can do something maybe like falling.
Absolutely, right? Bipeds, the easiest thing in the world to do, fall and slide down the declined plane head first, right? That's distance traveled down the declined plane. So the first thing, actually, what all of these terms are collectively doing is pushing this trade-off, is dealing with the cost that we need to pay for energy efficiency, which is stability, right? We need to keep this thing upright. Okay, so fitness, distance traveled, torque used here. Someone asked about energy efficiency. There is actually a bit of a penalty here for torque, which is when the CPG sends a signal to the leg is allowed to use its motors for a very brief period of time, which the details of which we'll talk about in a moment. We're going to try and minimize the amount of torque, the amount of force that the motors apply to the springs at that time. You'll notice all of these 5 penalty terms have the same form. They're 1 over 1 plus something. We're usually trying to maximize F. If we assume that all of t, x, z, r, and y, if we assume they are all positive numbers, then you should be able to convince yourself that we are trying to penalize, we're trying to minimize the amount of t, minimize the amount of x, minimize the amount of z, r, and y, right? Question?
In a sense like this, where is the distance measured from?
The distance is measured from the top of the declined plane, and then how far down the declined plane do you get?
But like where on the robot would it be measured from?
Good question. It does not specify here. Could be the center of mass, could be the hip. It's not quite clear. Which of these 5 penalty terms is penalizing for falling? There isn't one that explicitly says minimize falling. Can you figure it out?
You fall, don't your feet rotate a lot up to the axis?
Possibly, although you can also stay upright and rotate your feet quite a bit. I'll resist the urge to demonstrate some of these silly walks. What penalizes for falling here? Have a look at they gave you a hint here with the coordinate frame. So X is pointing off to the left of the robot, Z is pointing upwards, and Y is pointing forward. The direction in which the robot should travel forward down the declined plane. Which of these terms is penalizing for falling?
The hip's rotating about the x-axis.
Exactly. So here's our x-axis, which is pointing off to the left of the robot. And at the hip, if it's rotating about the x-axis, it's this rotation. They're trying to minimize this. So minimizing x will minimize falling forward. And it will also minimize the silly walk of backward, forward, backwards, forward, backwards, forwards down the declined plane. Minimizing z, rotation about the z-axis, is minimizing this one. So it's minimizing this silly walk, which is a perfectly fine way to get down the declined plane, but obviously not efficient, at least in terms of displacement. We're performing a lot of additional movements that we don't want. Feet rotation about the z-axis. So don't move your legs don't rotate your feet too much inwards or outwards as you move. And also minimize hip rotation about the y-axis. So if that's the y-axis, it minimizes this particular silly walk down the declined plane. Yeah. So as you will see as we continue on with this course and look at some more advanced evolutionary robotics experiments, they often look like something like this. Maximize this, but don't maximize it in this way, and don't maximize it in this way, and don't maximize it in this way, and so on and so forth. I don't know, but I'm going to guess that the investigators ran their experiment with F equals D, and they got falling. Then they probably added in the 1 over 1 plus x, which got rid of falling, and this silly walk. Then they got another silly walk. They put in another penalty term, another penalty term. It's like playing whack-a-mole, right? What problem are they trying to douse? What fire are they trying to put out with this particular approach? It's a problem that exists in evolutionary robotics and every single branch of AI. What is that problem's name? We've mentioned it a few times now in the course. Perverse instantiation, right? So perverse instantiation, when you're dealing with robots, you're usually in the ministry of silly walks. There's an infinite number of ways to get from point A to point B. You're trying to get energy efficient, fast, stable, robust locomotion, but not in ways in which, in retrospect, you would not have wanted that gate to play out. Yeah? Okay. When you get to your final project, and if for those of you that try and evolve behaviors other than forward locomotion, you are going to have to play the perverse instantiation game as well. You'll notice that they're multiplying terms here rather than adding them. Why is that more advantageous than just summing up terms? Why not d plus 1 over 1 plus d plus 1 over 1 plus x and so on? What does the multiplication buy you here?
I think if you add it, you'd actually be rewarding for, like, if you'd add 1 plus 1 over whatever, it would actually make enough to fitness go up.
If you're adding them, it's not reversing reward and punishment, right? We still want to maximize these 6 terms. We want these 6 terms to be as large as possible. We could just sum them.
It's letting the neural network just say it can't care about one and just ignore it.
Absolutely, right? So if we sum them, it makes it actually easier for the evolutionary algorithm to ignore some of these terms. Which ones are easier to ignore? And why does multiplying them force the evolutionary algorithm not to ignore them? I mentioned that we're going to assume that all 6 of these values, d, t, x, z, r, and y, we're going to assume they're all positive values. What's their likely range of values? It's kind of hard to say. We haven't introduced actual length units yet. Some of these values might have very narrower ranges than others. Some of them may range between 0 and 10. Some of them may range between 0 and 0.1. It's not really clear from this experiment, but it's probably unlikely that they all have more or less about the same range. T has to do with forces, and D has to do with distances. The rest of them have to do with rotations. Probably going to be very different ranges. If one of them has a much narrower range than the others, it's easier for evolution to ignore it, right? It makes less of a contribution if we're summing these 6 terms. If we multiply them together, doesn't matter what their ranges are, they're each going to have an equal impact on this product as we go. Make sense? Okay, just kind of a detail that might be helpful for you in your final project. Okay, so back to the details of this experiment. I mentioned there were 2 phases. There's actually 3 phases to this experiment. There's a lot of moving pieces to this experiment. In step 1, we're going to turn on our evolutionary algorithm. We're going to evolve these 22 body parameters to maximize F here. And during evolution, we're going to actually evolve these 22 body parameters. And I was kind of hiding this detail until this point. We're also going to evolve part of the neural network. We're going to evolve the synapses that lie between the CPG and the motor neurons. Right? By doing that, by allowing the CPG to quote unquote talk to the motor neurons, when we turn on the CPG, it can send a short message to the motors, and the motors can tug for a very brief moment on the springs, which will get the robot into action, and it will start now to fall down the declined plane. If we go back and look at the neural network for a moment, if we start at this CPG and we follow these synapses, we can see that they flow to the hidden neurons flow to the motor neurons, and so on. So there is a tiny bit of a brain in this robot. So the CPG turns on for a moment. It sends commands. It sends some signal to the motor neurons in the left leg. The left leg moves for just a moment, and then that's it. We're not even going to allow the CPG to send a signal to the right leg. It's going to send a short command to the left leg. The robot's going to jerk for a moment and start falling down the declined plane. Okay, so that's evolution. So we're evolving these 22 body parameters plus the synapses that connect the CPGs to the motor neurons. During a single simulation, we're going to put the robot at the top of the declined plane. We're going to supply 1 CPG pulse, which is going to cause the left leg to move for a moment. After that pulse, we turn off the network and we record how far down the declined plane it gets and how it gets down the declined plane. All good? Okay. The robot does not start at the top of the declined plane with both feet on the ground like you see here. A little detail here. If we go back and have a look at the experiment here, one of these is B sub y, which is the starting hip angle around the y-axis. I think this is a typo. I think this is supposed to be starting hip angle around the x-axis. If you look at the x-axis, it's the one pointing off to the left of the robot. I think it's the rotation of one of the legs. So I think the evolutionary algorithm is allowed to place the left leg at a particular orientation to start with. I think. It's a detail, maybe it doesn't matter too much. But we're allowing evolution to kind of set the initial conditions for this robot before we start evaluating it. Okay, so far so good? Okay, unfortunately this is a bit of an older experiment, and unfortunately they did not record any videos, which is a shame. You'll have to take the investigators' word for it that they did manage to evolve passive dynamic locomotion down the declined plane. Presumably, it looks something like this. Just to refresh your memory of what passive dynamic walking looks like. Okay. Okay, so they evolved. Eventually, they got a gate that looked something like what you just saw. At that point, they paused the evolutionary algorithm. They didn't stop it. And they made a few changes to the experiment. They made a few changes to how the evolutionary algorithm runs. And they made a few changes to how the simulation plays out. Let's have a look at evolution. So evolution continues as before. They're going to evolve, they're going to continue evolving the synapses that connect the central pattern generator to the motor neurons. They're going to continue evolving these 22 body parameters. But they're going to add, or they're going to multiply this product by another multiplicand, which is 1 over 1 plus v, where v is the difference in velocity between the way the robot moves in the passive gate and the way it moves in the hybrid gate. So they're going to play back this genome that contains synapses connecting Cpg to motor neurons and these 22 body parameters. They're going to play it back in the simulation twice, 2 different ways. The first way you just saw in phase 1. The robot's going to get 1 pulse, and then it's going to move down the decline plane. When they run the robot in hybrid mode, they're going to send 1 pulse of the Cpg to the left leg. The left leg is going to give a bit of a jerk. The robot's going to start to fall forward, and the simulation is going to time the amount of time it takes until the left heel strikes the ground. And this amount of time sets the frequency of the Cpg. So in most adult humans, our Cpgs run at about 1 hertz. For very young children that are learning to walk, they take lots of short, fast steps. They have a different frequency for their Cpg. Chickens have another one, and so on and so forth. So we don't know what the frequency for the Cpg should be for this robot. We also don't know what the Cpg frequency should be for different instances of this robot. Remember, we're evolving these body parameters. Some of them have large L. Some of them are very tall. Some of them have low L. Some of them are very short. We want the body itself to dictate the frequency of the Cpg. Make sense? Okay. So for each robot, we're recording the time until first heel strike. And at that point, we send a pulse to the other leg. Send a pulse to the left leg, send a pulse to the right leg. We now have our frequency. So at the next T, the Cpg is going to give another pulse to the left leg, right leg, and so on. And now we have the hybrid dynamic. We have a hybrid dynamic walker. And again, just to remind you of what that kind of looks like, here's Denise, the hybrid dynamic walker, where the motor gives a bit of an impulse force just as the stance foot, the one at the back, leaves the ground to give Denise a little bit of a push forward, and then the swing leg goes passive again. Okay. Okay, so you can think about taking a given robot and evaluating it in 2 different ways, with 1 pulse or with a hybrid dynamic approach. So for every genome, they can evaluate it on the decline plane in the passive mode. Then they evaluate it again in the hybrid mode, and they compute V, which is the change in frequency, or the difference in velocity of the movement of the robot down the decline plane in the passive and the hybrid mode. And we're trying to minimize, as always, V. We're adding in this term 1 over 1 plus V. We're trying to minimize V. We're trying to minimize the difference in the velocities of the passive dynamic walker and the hybrid dynamic walker. Yeah? So far, so good? Okay. The other difference we're going to make is as we continue the evolutionary algorithm on, we're going to gradually lower the declined plane, and we're going to keep measuring the difference between The robot, when it does passive dynamic walking down the declined plane, and hybrid walking on this increasingly lower declined plane. What is this strategy of gradually decreasing the declined plane? We've seen that strategy several times before now. It's actually relatively easy to walk down a declined plane in the hybrid mode. It gets harder and harder to walk in the hybrid mode as you have to walk on increasingly level ground. So instead of just dropping the declined plane all the way to horizontal in the second phase, we're going to gradually lower it. What is this strategy? We've seen it a few times now in this course. If something is difficult for the learner, or the evolver in this case, we gradually make things more difficult. Or we start things off easy and then gradually make things more difficult. Scaffolding, right? The training wheels on the bicycle. We've seen this a few times now. Okay. So over this second phase, the declined plane is getting lower and lower and lower. And the robots that are evolving are being increasingly challenged to exhibit passive dynamic walking when they're put on the declined plane, and to exhibit hybrid dynamic walking when they're put on an increasingly flat declined plane. Make sense? Okay. Again, unfortunately, no videos. You'll have to take my word for it that at the end of this second phase, they now have some version of this robot that is walking more or less like Denise, like the hybrid dynamic walker, on flat ground. Okay. As I mentioned before, when we were talking about Denise and the passive dynamic walker here, it took the roboticists months and months and months to get the details of these mechanics just right. Here's an example of where evolutionary robotics is useful. We've broadened the evolutionary algorithm to tinker with both body and brain so that we as the designers can take a step back. We don't have to determine the exact curvature on the feet of the robot. All we need to do is tell it generally what we're looking for and what we're not looking for. Makes the job of the designer a little bit easier. Okay. This is the experiment that just keeps on going. Once they had hybrid dynamic walking, they still weren't satisfied because this robot, although it's energy efficient, it's still not very robust. It wouldn't be able to deal with rough terrain or anything else that happens because it has no sensors. It's completely blind. So they're going to pause evolution again, make a few changes, and then turn the evolutionary algorithm back on, and now evolve sensor-based hybrid dynamic walking. How does that work? They're going to now, in the neural network, turn on all the rest of the network that was currently hidden, which are all the synaptic pathways that go from the sensors all the way through to the motor neurons. I'll just back up here for a moment. So remember that we have all the synapses that flow from the CPGs to the hiddens to the motors. Now we're going to turn on all of these synapses here. And we're going to start by setting all of those synapses with weights that are very, very, very close to zero. Why? Why not just add them into the genome with values between -1 and +1? Why add them into the genome, tack them onto the end of this vector with values that are very close to zero? We have a hybrid dynamic walker at the end of phase 2, which is able to walk on flat ground, although it's blind. It can't alter or modulate the way that it moves in response to proprioception, angle, touch, acceleration, orientation. We're going to try and give it that ability by adding in these synapses so that sensor values are now going to influence the motors that are pulling or pushing on the springs. But we're going to add in those synapses with values very close to zero. Why?
Because you want it to keep walking the way it was?
you want it to keep walking in the way that it did, right? If we suddenly threw in all these synapses with high magnitude, suddenly the robot would do something completely different. The motors would do something completely different than what they were evolved to do previously. This is, again, another trick that you can use in your final project. You can give the robot more and more sensors or more and more capabilities, but you don't want to break your partially evolved solution. So you add stuff in that has an influence close to zero. Synaptic weights that are close to zero. If evolution wants to make use of certain sensors, then it can mutate those particular synapses and increase their magnitude positively or negatively away from zero. Okay, so in our evolutionary algorithm now, we have a vector that has the 22 body parameters, which we had at the beginning. It's got the synaptic weights of the synapses between the CpG and the motor neurons, and now also all of those synapses between the sensor neurons and the hidden neurons. We've got a pretty long vector now, where now evolution can tinker with almost all aspects of the robot's body and brain. We're still using 1/1 plus v from the second phase, and during the evaluation period, we do the same thing that we did before. We evaluate a given robot on flat ground, and we compare the velocity, we compare its motion on flat ground in the hybrid mode against what it does in the passive mode when we put it on the declined plane. So in phases 2 and 3, we're evaluating every genome twice, once in the passive mode, once in the hybrid mode. So far, so good? Okay. At the end of phase 3, again, sorry, no video, but at least they gave us a plot of how the best robot moves. So time here on the horizontal axis is time steps in the simulation. You can see our CpG now in blue giving its regular pulses. And for this particular robot, the CpG is providing an impulse force every 37 time steps. That's how long it takes for this particular robot from t equals 0 to first heel strike. 37 time steps. So that's the frequency of the CpG. You can notice in pink and yellow how the robot is responding to the CpG. As always in this experiment, just to keep things easy, they're showing us just one leg. Assume the other leg is doing exactly the same thing. We can see that at the moment the CpG fires, the hip, the motor that's pulling on the hip, the motor that's pulling on the hip springs into action and pulls with a relatively strong force. It's not clear how exactly that's forcing the hip to move, but we can see that there is strong pulling on the hip, and then those motors start pulling on that spring less and less hard, and eventually they let go of the spring by time step 25. So it's a form of hybrid dynamic walking. It's maybe not as efficient as it could be. We could imagine the motor pulling on the spring very quickly and then releasing just as quickly. It doesn't release its grasp on that spring quite as quickly. In the case of the knee, it's a little bit more efficient. In yellow here, there's a motor that's pulling on the spring at the knee. It's pulling on it with maximum force at time step 10, and then lets go by about time step 20. And then you'll notice this flat in the yellow between time step 20 and time step 37. So the motor has stopped pulling on the knee. The knee is completely passive during this period. So we can see some hybridicity here. Some actuation and some passive dynamics. Yeah? Okay. Phase 4. This is the experiment that just keeps on going. They were particularly successful. At the end of phase 3, they have a robot that can exhibit hybrid dynamic walking. It's somehow this walking is being modulated by the sensors. Can't see from this picture how that's happening, but we can assume that it is. Phase 4 here, they're now going to continue evolving as they did before. They're not going to make any change to the evolution, but they are going to make a change during the simulation, which is as the hybrid dynamic walker walks on flat ground, they're going to introduce wind. They're going to start to apply small external perturbations that push on the robot and evolve the ability for the robot to keep moving in the presence of wind. At the end of phase 4, they now have a robot that is robust to increasing forces of external perturbations. Again, there's no units here, so it's not clear how strong these external perturbations are. But up to 4 here, the robot does exactly what it did in the presence of no wind. And as things get windier, this particular evolved robot starts to move more erratically, and after a while, it only takes 5 or less steps before falling over. Okay. In this fourth phase here, by evolving the robot in windy conditions, they're slightly altering or forcing evolution to alter the trade-off that these robots make between the 4 competing factors in locomotion. How is it forcing evolution to change that trade-off?
It makes it like momentarily have to prioritize stability.
It has to prioritize stability. Remember Big Dog and Big Dog getting kicked in the side? Big Dog has to sense that there was a change that occurred. So this robot and Big Dog both have to make use of their sensors to know I am now falling, and if I don't do something in the next 2 milliseconds, I'm in real trouble. So in phase 4 here, the robot is learning to be more stable and also more robust. It's able to continue walking in windy conditions. So we're actually moving towards a gait which is more stable and more robust. And as always, we're going to have to pay a cost somewhere with these other trade-offs. How does this robot pay for this ability to become more robust and more stable? Again, I don't have a video to show you. When you walk in very windy conditions, what cost are you paying to keep upright and keep going? You slow down. Yeah, that's one strategy. You can't slow down too much, though, or else you'll never get where you're going.
What would be the rotation of joints?
Sorry?
The rotation of joints?
The rotation of joints here has to change, right? You have to modify your gait somehow, which means...
Oh, no, I was going to say energy.
Absolutely, right? You have to use more energy. Energy efficiency is great. If everything is stable and exactly the same, you can get away with, you can actually tune your hybrid dynamic walking to be very, very passive. But when things change, you got to change the rotation of your joints, which means your motors have to do different things, which means the motors need to know how to change in response to sensors, which means you got to pay a little bit more in terms of energy. And you need to get a little smarter. When Big Dog was kicked, or when you're kicked, or when you trip, or when you miss a step on a stair, there's basically an infinite number of ways that you could send commands to your motors over the next 2 or 3 milliseconds. And a vanishingly small subset of those commands are commands that are going to rescue your fall. This is one of the places in which intelligence starts to creep in. If you need to get from point A to point B, especially in a complex world, it is not a trivial matter to do so. You have to very quickly choose the right strategy among an infinite number of wrong strategies, possibly dangerous strategies, possibly life-threatening strategies. This is the point at which we start to move from a discussion of locomotion into a discussion of intelligence. Okay. Again, the experiment that keeps on going. Phase 5. In this case, they continued evolving the robot, but every time they quote-unquote built the robot in the simulator, they introduced mistakes. Sometimes they made the leg a little bit longer than it was supposed to be, or a little bit shorter than it was supposed to be, as you can see in the bottom left here. You can understand why the experimenters would want to evolve robots that can deal with windy conditions or walking down declined planes or flat. Why would you bother doing this? Why evolve robots that are robust to internal perturbations, manufacturing errors? Seems weird. What's the utility in this?
Well, it's like we have like genetic mutations that slightly change the way that like our bodies work or grow or develop or whatever. So maybe they were trying to see like if the same network could adapt to mutations.
Absolutely, right? So no two bodies are exactly the same. So whatever strategy we have to learn the biomechanics of bipedal locomotion, it should be robust to different bodies. So maybe it's they're testing some biological hypotheses here. There's also a very good engineering reason for why they did this. What might that be?
If you're going to take this and try to put it into an actual physical robot, there are going to be manufacturing mistakes.
Absolutely. So next week, we're going to spend a lot of time talking about sim to real, which is probably the biggest challenge in robotics. Almost everything we've seen in this course so far has been in silico, which is all well and good, but eventually we want to build real robots that do real useful work in the real world. And as you mentioned, no matter how fancy your 3D printer is, when you come to print or build this robot, there are going to be errors. If we build a physical version of any one of these in silico robots, there are going to be differences between the physical version and the simulated version. We can be proactive and we can prepare for those differences by, again, evolving robots that are robust to internal perturbations. So here we go. They evolve, and at the end of phase 5, they take the best robot, the one that had the highest value of F. They play back that robot over and over again in the hybrid mode on flat ground, but now they introduce increasing percentages of manufacturing mistakes. And you'll notice that, I guess up until maybe 15%, the robot's still taking 30 steps. That's pretty good. A manufacturing mistakes of 15%, that's a pretty crappy 3D printer. But just for fun, they wanted to see how far they could push this process. The robot's still taking 10 steps when there's 50% manufacturing mistakes. The robot may be half as tall or twice as tall as it was before. It may have, the manufacturing errors may have hit these mass blocks. You may originally have evolved to be front heavy, but now suddenly you're back heavy. And still, it's able to take some steps before falling over. Okay, they ended evolution at this point. The last part of this experiment, just for fun, is they took that best robot from the end of phase 5. It's robust to passive and hybrid walking. It's robust at this point to declined planes, flat ground. It's robust to no wind, some wind. It's robust to no manufacturing error, some manufacturing error. And they introduced they threw one more curveball at this one evolved robot, which was to tune up or tune down the frequency of the Cpg. You can see the results here. So it's kind of hard to see. It might be difficult to see from the back. We're going to play this horizontal axis here. This is time steps in the simulation. At the beginning, you'll notice that the Cpg is firing every 35 time steps, which makes sense for this robot. They then started to slow down the Cpg a little bit. It's difficult to see in this plot, but actually if we look at the tops of these peaks, you might be able to see it a little bit better. Let's see. I'm sorry, here we have these 35 time steps, and during this period, they started to actually speed up the Cpg. Hopefully you can see the horizontal widths between these peaks is getting less at this point. It's a little hard to see. CPG is firing a little bit faster during this period. How does the robot respond? Taking smaller steps. If you go back to the beginning of lecture 11, we looked at that. That's an adaptive strategy that we often pursue as well. There's certain conditions where you want to take short, fast steps. In this last third, you'll notice the horizontal distance between neighboring peaks is increasing. They are decreasing the frequency of the CPG. The CPG is firing at a slower frequency. And how does the robot respond? Longer steps, right? Slower, longer steps. Where in those 5 phases was there pressure to evolve robustness to CPG frequency? I see some of you shaking your heads. Nowhere. There was no fitness term that's selected for robustness to CPG frequency, but this robot is robust to some degree to CPG frequency. Where is this coming from? It's the very last point we're going to make about this experiment. Why? Why is this robot robust to CPG frequencies? It was never evolved to do so.
Well, wasn't it kind of, because what about the CPG neuron that is the network?
Okay, so there's this CPG network, there's this CPG, let's go right back here. There's this CPG neuron up here. And remember that for each individual robot, that CPG is going to provide a particular frequency, right? It's up to the robot. In essence, the robot dictates, I move at this frequency. So each robot has its own CPG frequency, but what we're seeing in this last picture here is one robot that has a preferred frequency, which is 35, but it seems to be able to handle frequencies faster than 35 hertz and slower than 35 hertz. How?
Would the angle of the slope have something to do with it? If it's like a downhill, your strides would be longer and your strides would be shorter.
Maybe. Think about all the adventures that this robot has gone on at this point. This particular robot with these 22 body parameters and these synaptic weights, it may never have actually existed in phase 1. Maybe only its great-great-great-great-grandparent did. If you think about the ancestors of this robot, the ancestors had different bodies, they experienced different environments, they had different synaptic weights, they had different brains, but they all survived in their niche for long enough to produce offspring, which also survived in their niche to produce this particular robot at the end. So this robot is a twig on probably a tree that goes all the way back to the very first phase of this experiment. And we need to think not so much just about this robot, but the robot's parent or parents, depending on whether they used recombination, grandparents, great-grandparents. Indirectly, this robot has inherited the robustness of all of its ancestors in the same way that we all have as well. None of us obviously have experienced the breadth of experiences that all our ancestors have. Even though we didn't directly inherit those experiences, there's something in our DNA or the DNA of our families or our ancestors that made us particularly robust to perturbations. The reason we're spending a few minutes talking about this is, again, we're transitioning now from a discussion of the nuts and bolts and biomechanics of locomotion to intelligence. We now have a robot that is robust to changes in its environment. It knows what, it quote unquote knows what to do when the environment changes, possibly the external environment like wind, or the internal environment like changes to a CPG. And it inherited that robustness because its parents were robust and its grandparents were robust and so on. So this robot somehow seems able to take on new challenges that none of its ancestors ever saw. You are currently taking on the challenge of learning evolutionary robotics. I can be pretty confident that your parents probably don't know what evolutionary robotics are, never learned it. But you're learning it. You're able to learn things and operate in environments that your ancestors never saw. Again, another important hallmark of intelligence. Okay. Any questions about this experiment or this theme before we move on to our new theme in challenges and open problems in the field? No? Okay, so challenges. We're going to spend in the next 13 through 25 lectures. We're going to look mostly at questions, and we're going to look at partial solutions. People have had some answers or attempts to solve these problems, but all of the problems that we're going to talk about here are still unsolved. We'll spend the last 9 minutes of class today talking about the open problem of modularity. Think about the neural network we just saw in that biped. It's basically a ball of spaghetti. Everything is wired up to everything else. If you allow your evolutionary algorithm to not just tune synaptic weights, to tune the weights of synapses, but actually add and remove synapses, what an evolutionary algorithm always will do is tend to add more and more synapses, make a neural network less and less modular over time. Your brains, your central and peripheral nervous systems are very modular. Every neuron in your brain is not connected to every other neuron in your brain. It's connected on average to about 10,000 other neurons. Sounds like a lot, but given the total number of neurons in your brain, our brains are quite modular and quite sparse. Not everything is connected to everything else. When we evolve neural networks, or in machine learning, it's called neural architecture search. When you're searching for a good neural architecture, they tend to become less modular over time. Evolution or machine learning tends to paint itself into a corner. It makes things less and less modular, which makes it harder for evolution or machine learning to make changes to that system. If you have a very non-modular system, you make some change at some place, that change propagates everywhere, the machine typically breaks. We'll talk about that today. Next time we'll talk about a very famous pair of algorithms in this field, neat and hyperneat, which are actually partial solutions to a problem that we haven't talked about yet. We'll talk about that in lecture 14. As promised, we're going to spend 6 lectures talking about crossing the reality gap. We evolve simulated robots, we build them in reality. They don't do anything close to what we saw in simulation. How do we cross the sim to real gap? We'll spend 2 lectures talking about how to try and scale up evolutionary robotics. For all of you, there's going to be one researcher that's going to make one evolutionary robotics experiment over 3 or 4 weeks. You'll post a video on YouTube, and that'll be the end of it. How do we start to do evolutionary robotics experiments where we have populations not of hundreds of robots, but millions of robots? We have thousands of fitness functions. We have thousands of participants coming up with fitness functions, tuning fitness functions. If we want robots that are practically useful in the real world, we're going to have to get away from these toy experiments of one person tinkering with one fitness function that evolves one type of robot. An obvious solution for doing this is crowdsourcing. How do we open up evolutionary robotics to the crowd so everybody can participate in trying to deflect an evolutionary algorithm towards good robots and away from dangerous robots? We'll then talk about, that'll finish our discussion of open challenges. Okay, so that's sort of an overview of where we're going. So let's start with modularity. And we've got 5 minutes left, so we'll just kind of introduce the problem, and we'll talk about the solution next time. Modularity is ubiquitous in engineering. It is, if you were to ask an engineer, what is the most important rule in building or making something? An engineer who's paying attention should probably give you back the answer of modularity, right? Otherwise known as divide and conquer. Okay. It comes up in lots of different domains. It has very different concepts and terminology. But the basic idea tends to always be the same. You have something like modules. You have components or modules, and there is tight coupling within a module and less or no coupling between modules, right? You open up your computer, there's the memory module, there's the CPU. You open up the hood of your car, there's the engine, there's the muffler, there's the this, the brakes, and so on, right? It's everywhere in everything that humans make, including software, right? You just did a fair bit of object-oriented programming and refactoring. What you were doing in refactoring, hopefully you succeeded at this, was creating modules that correspond to the basic concepts in evolutionary robotics. Robot, solution, optimization, body, brain, neuron synapses, and so on. Why do we want modularity? We want modularity because as we're designing a series of machines, and these machines are getting better and better, if we change or remove a module, we want that to have little effect on the whole thing, right? If you make a change to your code and that causes changes on almost every line on your code, you're never going to debug that piece of code. Okay. With the proviso that some modules tend to be more important than others. Even in a modular system, if we're tinkering with a critical component, that can often have global effects. Okay, so the whole challenge in becoming a good programmer is getting really, really good at OOP, object-oriented programming, in which you're trying to hide the internal complexity of a given class or a given class instance from the internal complexity of another component, right? In your case, hopefully you now have a relatively modular code base where you can relatively easily swap out the hill climber and replace it with a parallel hill climber. Swap out the parallel hill climber, replace it with a genetic algorithm, and so on and so forth. Okay, this is some C code, not Python code. You get the idea. Okay. Modularity is ubiquitous. It's everywhere. If you take engineering courses, you will study all aspects of modularity. There are different kinds of modularity. We've actually talked about these two different types of modularity already a few times throughout this course. Structural modularity is the easier kind of modularity to think about. If you think about a neural network, you have a bunch of neurons. We're going to wire up every neuron to every other neuron. We have n times n minus 1 synapses, right? The number of synapses grows quadratically with the number of neurons. If the number of neurons n grows, the number of synapses n squared increases quadratically. Yeah? Okay, that's a non-modular neural network. When we're trying to design the architecture of a neural network, we're trying to make it more modular. We're trying not to wire every neuron up to every other neuron. Functional modularity is a little less obvious. In functional modularity, we have something that may be structurally modular or not structurally modular. It may all be wired up together, but that system can fall into discrete modes or patterns. The pattern inside that network holds for a while, something changes, and it falls into a different discrete pattern, and so on. We saw that when we saw functional modularity when we talked about the little humanoid robot that was shaking the block up and down, then left and right, then forward and back. Those are 3 different motor primitives. We had a relatively structurally non-modular network. We had a whole bunch of neurons wired up, but they exhibited functional modularity. To finish today, I want you to think about neural networks that are structurally modular but not functionally modular, functionally modular but not structurally modular, and so on. You have a quiz due tonight. You're starting in on assignment 9. See you back here Thursday morning. Have a good rest of your day. Thank you.